We have many who are still trying to join, so as we give a few instructions, we'll give them a moment or two to all get online. We do have a large registration today, so it may take a little bit for everyone to get in and get hooked up. If there are any issues with anybody with listening through your computer, Haley Rich, our wonderful technician, has posted the call-in number that you can dial into using your phone or headset instead of the computer. And again, the presentation, the WebEx, is as good as your internet connection, so sometimes it is easier to hear if you dial in using the dial-in number. So check the Q&A panel, check the chat feature, and the number should be posted in there if you're having difficulty hearing from your computer. All right, well, for those of you who are joining us for the first time, my name is Susan McCorvey with Cleaver Brooks, and Cleaver Brooks hosts a webinar. Usually we hold one once a month. Sometimes we skip a few here or there. We do these at the request of topics that are among interest to our viewers. So if there is a topic that you would like to hear from, be sure to let us know through the chat feature, Q&A tool, or the wonderful survey that comes to you when you close out of WebEx. Today's presentation is on boiler condensate return basics, and it will last about 45 to 50 minutes, and we'll have a few minutes at the end to have questions with Steve Connor, who is on our expert panel, as well as the presenter for today. If you've missed our previous presentations, they are located on our website, cleaverbrooks.com/webinars, and we have about 3 or 4 years worth of great presentations there, so feel free to check those out. So at the conclusion of today's presentation, we'll post this as a recorded version along with a PDF of the PowerPoint, and you'll be able to access both. If you requested a certificate of completion through the registration process, we will have that emailed out to you. It usually takes a day, but by Friday for sure. If you have not requested one or can't remember if you requested one through the registration process, never fear. You can email us at marketing@cleaverbrooks.com. Just let us know that you would like a certificate of completion, and you can use that to submit for your credits for professional development hours if you choose. And for those of you that are watching together but registered under one email, just send us a list at marketing@cleaverbrooks.com and just telling who is viewing, and make sure we have their email address and title, and we can send them a registration, send them a certificate as well. With that, let me see if we are slowing down on our, they're still popping in here. Steve, you've got a large crowd today, so happy to hear that everybody is taking times out of their busy schedule to join us. Steve, I'm going to go ahead and turn it over to you. Again, if you have any difficulty, please use your WebEx control panel to ask questions using the Q&A tool or the chat feature, and please put it to all panelists. That way, if it's a technical issue, you can have Haley get on it. If it's something else, maybe I or Steve can help as well. So again, use the Q&A tool or the chat feature and put it to all panelists. And now, Steve, I am going to start the recording, and I'm going to hand it over to you.
Sounds very good, Susan, and thank you very much. And thank you all for joining us. And the fact that we've got a large audience today is really it's really good to hear, and I'm so pleased about that. We all are. Today's webinar is, it's actually a continuation of the webinar that we did back in November, and I think the solicitation that went out mentioned that. And that's where we talked about the steam supply basics. As some of you who attended will recall, the emphasis was on steam supply piping and how it's all integrally connected, including, of course, the boiler, which is the heart, then the piping, various control valves, and the steam trapping devices, all of which are there to allow the steam to safely and reliably reach the end user. The use being heating, process, or maybe it's both heating and process. So today we're going to essentially pick up where we left off in November and talk about the piping system, which returns the medium back to the boiler room and back to the boiler ultimately after it's completed its work. Of course, I'm talking about the condensate return piping system and including its various components and critical elements that are needed for its effective and its safe handling. So this is what we'll be covering today. A brief review of the total system. That's just to kind of get us oriented again based on the total integrated system, both supply and return. And then why a proper condensate return system is so important. Condensate return and effect on the properties operation, whether it be heating, whether it be process, whether it be both. The return system and its effect on the properties operation. And then what compromises the optimum condensate return system, and then how do we correct these compromises, if you will. Then we're going to talk about delivering condensate back to the boiler room and the choices for holding and treating this condensate. And then we'll get into a summary. At least this will be a list of the takeaways I think that are really important for today. And then, of course, we'll conclude it with the Q&A as we always do. So, as I stated, I thought it would be good to start, as we did the last time, with an overview of the entire steam system, starting with the boiler in the lower left corner, as you see there, and then progressing through the red piping line where the steam is serving various uses, including process and heating. And then once the steam has done its work, in other words, it's given up its latent energy and transferred the motive force and or the heat to its user, it then condenses and is returned to the boiler room through the blue line. This is, of course, what we'll be discussing and talking about today. And you know, when we talk about the total steam system, and as mentioned the last time, it's very analogous to the human body, with the arterial system laden with purified and oxygenated blood from the lungs, flowing to the various extremities and organs within the body and nourishing them. Then once the blood has done its job, it's returned through the venous system, passing through the liver and lungs, where it is now ready to repeat the cycle. So it's the same with our steam system. The arterial system is the steam supply piping, including all of its components, serving various users. And then the venous system, the condensate return system, returning this liquid gold along with any makeup through the purifiers, which would be the liver, which in the case of the steam system includes the boiler feed system, which could be a vented receiver or a deaerator. Then, of course, the water softener and the chemical feeding device. And you can see the liver there in the middle of this screen, and then the arrows pointing to the three systems I just mentioned, or mechanical accessories, the water softener, the chemical feed, and the deaerator, with the arrows pointing to those. So, okay, so now I guess it gets to the question of, why is understanding the condensate return system so important? I mean, why not just waste it? Waste the condensate and save all the piping and the component costs. Well, you know, the answer lies with these three primary reasons. Operating cost reduction. In other words, let's improve the overall system efficiency, reduce the fuel cost. Then, of course, we have a reliability issue as far as the process or the heating plant is concerned, and then safety. Those are the three reasons why, general reasons why, we want to return condensate. Take care of it. All right, let's start with increasing efficiency and thereby reducing the cost of operation in our process plant or in our facility that we are heating, maybe through a campus central steam plant. Or possibly it's a hospital, which needs steam for its autoclaves, it needs it for the kitchen, maybe a laundry, and it also wants to heat the building with steam hydronically, in other words, through a secondary heat exchanger. Whatever the case may be. And returning, you know, to my old standby slide, which reflects the cost of fuel in a typical facility, you can see where fuel plays a significant role in overall cost. Now, I'll hasten to admit that the cost of fuel has dropped dramatically since, let's say, 5 years ago when $15 per 1,000 pounds was considered acceptable. It's probably half that today. Maybe it's $8 or $5 per 1,000 pounds. But, it's a very competitive world that we're living in today. And all industries are looking at ways to remain relevant. And reducing fuel cost is still a very viable piece in the puzzle to remain price competitive, to say nothing about the positive impact that saving energy will have on our environment. Now, to get a handle on how the energy-saving piece works, I think it's good to revisit how a pound of steam is formed. And for brevity purposes, I'm going to start with feed water coming into the boiler at 200 degrees Fahrenheit. And the boiler operating pressure is at 100 pounds per square inch gauge, 100 psig. Now, referring to any steam table, you will find that at 100 psig, water is saturated at 338 degrees Fahrenheit. In other words, this is when it gets to boiling point. This means if any more heat is added in the form of BTUs, it will change state and become steam, which is what we want. And that is why at the bottom of the chart, you see we added 138 BTUs per pound of water to get to saturation from the beginning point of 200 degrees. That's the sensible energy. This is called adding sensible energy. And the sensible energy component is essentially the BTUs in the condensate. Then to the right of the 138, you see 880 BTUs per pound of latent energy. This is the energy required from the burner to produce a pound of steam at 338 degrees Fahrenheit, the same as the water temperature. This latent energy is what goes into the process before the steam condenses. Now let me show you another slide just to drive home this point. Here you see an abbreviated steam table, which I think clearly exemplifies the point that I'm trying to make here. Note the pressures across the top horizontal, going from 0 psig to 100 psig. And then follow the red highlighted sensible heat line as we go from 0 gauge pressure to 100 pounds. The sensible BTUs required to produce a pound of steam at the increasing pressure continues to rise. Remember, this is the liquid form of that pound of steam, and it represents condensate, which could be returned, saving the burner from having to make up those BTUs, that BTU debt, and of course that saves energy. And there's another way to look at it. All we boiler manufacturers, whether it be Cleaver Brooks or any other of our worthy competitors, rate our boilers at 0 pressure gauge per square inch and feed water coming into the boiler at 212 degrees Fahrenheit. This is the benchmark. Referring now to the red arrows on the screen, you see 0 gauge pressure and arrows pointing at 212 degrees Fahrenheit, which is the way we rate the boilers, and 200 degrees Fahrenheit. The 212 degree Fahrenheit arrow represents the normal boiler rating, meaning under these conditions, the boiler will produce 34.5 pounds of steam per hour, which we always refer to as a boiler horsepower. Now, dropping this temperature slightly, just to 200 degrees, you see a slight drop in output. We've gone from 34.5 to 34.1 pounds per hour. But if we drop it to 100 degrees Fahrenheit, as highlighted in the blue above, it drops to 30.9 pounds per hour. Now that's 11% drop in capacity. So feed water temperature becomes very important, not just for saving energy by returning condensate, but making the rated capacity and matching the required load as well. Now, the other thing that you need to keep in mind is the rule of thumb that you can take to the bank. For every approximate 10-degree drop in feed water temperature, you've lost 1% in efficiency. And what you see on the screen now, with what appears to be a leaking pipe, it's actually an open condensate line exhausting liquid gold to the atmosphere. This is costing this company thousands of dollars annually. And in many cases, no one is aware, or most tragically, in some cases, they just don't care. Hey, gas is cheap today. believe me, the days of 22-cent per therm gas, or $2.20 per decatherm, and oil at $30 or less, it's not going to stick, and you know that. It's all going to be rising as soon as this glut that we have in this world is exhausted. And you know, along this line, what never ceases to amaze me, and this is nothing to do with recovering condensate per se, but when we have situations where there is considerable continuous blowdown coming from the boiler to maintain the proper total dissolved solid, or TDS level in the boiler, why this effluent coming from the boiler is not passed through a heat exchanger, transferring the heat to the boiler makeup water before going to the feed tank, be it a vented or a pressurized receiver, is just beyond me. Maybe it's just never thought of. But getting back to the condensate recovery, the other thing that is normally overlooked when not returning condensate is the loss beyond the fuel cost. What about the chemicals that went into that pound of water, which is now wasted? And the water and sewer charges incurred, which only go up as raw makeup is introduced to account for the condensate lost. Okay, so those are the major considerations concerning a properly designed and operating condensate return system as it relates to reducing fuel costs by increasing efficiency. But what are the reliability issues? Well, the reliability issues start with the way the steam is applied to the system, be it for heating or let's say process. You see in the top left corner of the screen, the steam control valve, which is metering steam to the user based on a varying load. Let's say it's a jacketed kettle or a heat exchanger, either a shell and tube or a plate and frame heat exchanger. In any case, the steam is giving up its latent energy and the condensate liquid is forming. Now, as the regulating valve modulates from full open to partially closed, the pressure in the heat exchanger drops. And this often affects the differential pressure across the trap, not allowing it to fully evacuate the condensate. Now, as the condensate backs up, it causes a couple of problems. First of all, the shell of the exchanger begins to flood, and we lose heat exchange to the product being heated because of a lack of heat transfer coefficient. And in so doing, and with a process application, we also lost production as well because the product has not reached its sterilization or pasteurization value. So production stops, and most probably the product is dumped. It's just dumped, further driving up production costs. And as you can see on the top of this slide, this phenomenon is referred to as stall. So, okay, and this happens a lot. What's the remedy for this? Well, and this happens, one thing that we could do is put a small orifice trap at the bottom of the heat exchanger and continuously purge the condensate to drain. Not very energy efficient, but it works. Or we could install a properly sized steam power pump system, which is nothing more than a large floating thermostatic trap with another steam trap downstream of it. Now, as you can see, with this arrangement, steam and condensate are present in the steam pump, and as the condensate collects within it, the float rises and allows this pump to evacuate the fluid, and then steam re-enters as the fluid is evacuated, the condensate. Then during full load conditions, where normal condensate levels are present, in other words, that steam control valve is full open, the trap downstream from the steam pump handles this load. So it's only under those low load conditions where the downstream trap has lost its differential where the steam pump comes into play. It works very well and certainly helps that reliability issue and problem that we talked about. Now, the other problem we have to concern ourselves when considering condensate forming in heating or process loads is the possibility of vacuum. Remember, when steam condenses, we have a severe volumetric change, sometimes as much as 1,600 time reduction. So if this is a possibility, a vacuum breaker needs to be placed at the source of the exchange to prohibit this from happening and allowing air to enter the exchanger, replacing the void. Now, this too causes a couple problems. First, we've lost the differential across the trap because of the drop in pressure in the shell and tube exchanger, not allowing the condensate to evacuate. So in this case, or eventuality, you need to assure that you have sufficient water column above the trap inlet, in other words, static head, to provide the pressure differential needed. Remember, you need 2.3 feet of vertical water leg or head above the trap to give us 1 pound of pressure. And this is called, I'll mention it again, the static head required. Now, the second issue is how do we handle the air which now entered into the heat exchanger? Remember, air will dramatically reduce heat transfer due to what we refer to as partial pressure. You have a pressure, but you don't have the temperature because of the air. So we need to get rid of it just as quickly as possible. And of course, that is done by using thermostatic air vents, which are strategically placed at the users as well as high points in the system, and that's now shown on the screen. Because from a reliability perspective, this is extremely important, and not just because production will be halted because the product is not being sufficiently heated, but for another reason as well. And that is the corrosion the dissolved gases will have on the carbon steel or iron surfaces when they come in contact with them. And as you can see, I'm talking about oxygen and carbon dioxide. But also note, heat is an accelerant for oxygen corrosion. The higher the temperature in the heat exchanger and in the piping, the more aggressive the corrosion becomes. Now, in this particular example, we're going from 86 degrees Fahrenheit to 122 degrees. And the corrosion rate doubles with this 40% increase. And that's why we need to get rid of the air, which is 10 times more corrosive than the carbon dioxide. And speaking of carbon dioxide, it initially comes into the boiler through the feed water supply as carbonates of alkalinity, carbonate salts, and resides as part of the boiler's TDS. The problem is, when the water evaporates, steam is formed, and goes out to do its work and then condenses, CO2 is formed, combines with the cooler condensate water in the piping, and becomes carbonic acid, H2CO3, carbonic acid, which will attack the condensate return lines. And if oxygen is present as well, it becomes even more aggressive. It's pretty nasty stuff, which, silently eats away at the return piping, attacking the weakest portions of the piping first, like the threaded connections, but then also causing wall thinning by forming grooves, as you see in this picture now. And this weakening can also lead to extreme cases where you have a high-pressure condensate return line, and it's precipitating actual splitting of the pipe wall, causing not only a major safety issue, but a significant loss of energy to wasted condensate and, of course, a stop in production. So how do we stop this from happening? Well, what we have found over the years is the best overall answer is having a solid water treatment program incorporating both mechanical and chemical means. For instance, mitigating condensate line corrosion starts with limiting the carbonate and bicarbonate alkalinity to begin with by maybe using a dealkalizer. Or maybe it's a real solid amine neutralizing or filming amine dosing program, which is injected into the steam supply header so that when condensing occurs, we have an agent present to arrest the problem. Or, maybe it's a combination of both the dealkalizer and amine dosing, which are just working together in tandem. And it's a very important issue which needs to be discussed with a reputable chemical treatment professional. All right, so far, we've talked about some of the key issues concerning why and how condensate impacts efficiency, reduces operational costs, and reliability. But, I would be remiss if I didn't spend at least some time on the proper capturing and transportation of this most precious commodity before we get into the last important issue involving condensate, and that's the safety issue. You see, it really all starts with what I mentioned back in November, providing the driest, liquid-free steam to the user as we possibly can. And that many times involves the use of a steam separator, which separates the entrained water droplets using 3 optional methods, as you see on the screen, and then sending them to the condensate return line. Now, here's a piping diagram showing you where the separator is typically placed in the steam supply line and how the liquid and condensate flow to the return line downstream of the trap, as indicated with that lower red arrow saying to condensate return line. The other thing we need to concern ourselves with in referring back to the steam line is the placement of adequately sized drip pockets to capture the condensate as it forms in the header. I discussed this subject at length during the November webinar, so I certainly won't belabor it now, but suffice to say, in addition to the drip pocket, you see the recommended steam trap set consisting of the isolation valves, the strainer before the trap, the steam trap, and the check valve on the discharge side of it. And another thing I wanted to draw your attention to, because it's so important, is the frequency of the drip pocket placement in a linear length of pipe. Every 150, no more than 300 feet, as well as other locations noted in the red box. Also note the steam trap, its location, the total set location, is about 6 inches above the bottom of the drip pocket to allow for sediment to form, and that can be periodically blown down during normal maintenance routines. Of course, we want to do that because we don't want to get the scale and dirt sediment in the trap. Before leaving the drip pocket, I did want to again show you what I covered last November and what is the minimum size and length of these pockets or drip legs, as they are sometimes called or referred to, and that's relative to the steam header to which they are affixed. Note, these are minimums. In fact, I've spoken with some steam experts whom I really respect, who say they go with 8-inch pockets from the 8-inch steam line through 16-inch steam line. It's all about making sure that the condensate in the line is properly and completely drained. And, of course, that relies into the amount of condensate that you have, or that relies on, to get into the drip pocket, and also the velocity. So really, quite frankly, the bigger the pocket, the better off you are. Okay, enough of that. Let's now turn our attention to moving this valuable condensate that we've captured back to the boiler room. As you now see on the slide, one of the ways to move condensate is through the sheer motive force of the total steam system, wherein the differential between the upstream versus downstream pressures in the piping system moves the fluid to the proper holding tank in the boiler room. This happens sometimes, but it's really kind of rare for any number of reasons, which I won't get into today. Therefore, what is normally required is the use of a condensate transfer tank, as shown in the picture now, and there could be several of these dispersed throughout the facility, capturing condensate at various points and then delivering it to a common return line going back to the boiler room. Now, as you can see, these systems include an integral pump, a motor, and a tank, a complete package. And they're normally limited with regard to incoming condensate temperatures and the NPSH requirements. However, exceptions can be made, allowing higher temperatures and lower NPSH requirements. So it pays to inquire before spending the money for something that fails in a very short time. Okay, so now we have gathered the condensate and are going to pump it back into the boiler room. So what are the considerations? Well, one of the important things that we need to consider is the velocity of this fluid within the pipe, which will be determined by a number of factors, starting with the boiler's operating pressure. Then we have to know the amount of condensate that is being trapped, the pounds per hour that is being trapped. Every pound of steam, remember, becomes a pound of water. Then we have to know the pressure at the respective trap's inlet. We have to know the resultant pressure in the condensate line. Remember, we've got all these lines dumping into one common. Then we have to consider the condensate pipe diameter. And finally, the allowable pressure drop. That's the allowable pressure drop through that condensate return system, which, as noted, should not exceed 20% of the boiler's maximum operating pressure. Remember, this boiler is providing the motive force. And now going back to the total steam system slide again, you see drip traps at various locations feeding into the common. And they are all at different temperatures depending if the user was at low or high pressure when the condensate was trapped. This is how biphase flow is generated, because it is the amount of flash steam generated as a result of the difference in temperature between the trap's discharge and the condensate line's temperature and pressure. So the condensate is a combination of liquid and steam. And the amount of flash steam in the condensate pipe can be as high as 90% or more. And the more the steam, the greater volume of biphase fluid in the pipe. Which brings up another very important point to keep in mind. And that is the relationship between a pound of liquid versus a pound of steam, and the effect that pressure has on the steam volume. Looking at the steam table again, but focusing on the volume per cubic foot line, you see under the zero gauge pressure column how a pound of water expands when it goes through a phase change and becomes steam. Now, the small number, 0.017, below the 26.4, is the volume of a pound of water at 212 degrees. And when it changed to steam, it occupies 26.4 cubic feet, or approximately 1,600 times more volume. Then, as we increase the pressure, going from 0 to 10 to 80 and 100 pounds, you see how the volume of the pound of steam decreases, which is why in steam pipe distribution systems, the higher the pressure, the smaller the pipe size, while still maintaining the proper velocity in the pipe. And you know, it's the same with condensate piping too. And just like steam distribution piping, we need to keep condensate piping velocity in mind, which normally ranges anywhere from 3,000 to 12,000 feet per minute, with 3,000 to 7,000 being the preferred range to stay within 3,000 to 7,000 feet, or lower than that. The lower the better, if larger pipe cost is not a factor. So, to try and tie all this together in terms of selecting the right condensate pipe size for an application, let's just assume for a minute that we have 2,000 pounds per hour of condensate that we need to return. And we do not want to exceed 7,000 feet per minute in velocity with a 1/4 pound pressure drop per 100 feet. And our motive, as far as our motive force is concerned, we have 150 pounds of supply pressure while discharging into either a zero pressure condensate line or a 15-pound condensate line. Now, looking at the chart and the respective arrows, you see the first condition, which is 150 pounds into zero pressure and a 1/4 pound pressure drop limitation. Now here we can pass 2,100 pounds per hour while maintaining no more than 7,000 feet per minute velocity, but it needs a 2.5-inch line. If, on the other hand, under the same conditions, but discharging into a 15-pound condensate line pressure, we can discharge 2,350 pounds into a 2-inch line. Well, why the difference? Well, it gets back to that volume issue again, and the relationship of volume to pressure. At the lower discharge pressure, 0 pounds, the flash steam will increase volumetrically, and as such, if we want to maintain a 1/4 pound drop per 100 feet and stay within 7,000 feet per minute velocity, the line size needs to be 2.5-inch. Whereas with a 15-pound discharge, we have less volumetric expansion and therefore a smaller pipe size requirement while moving more condensate, all else being equal. Okay, so far we've addressed the important areas impacted by returning boiler condensate, specifically improving efficiency and reliability, and in so doing covered a brief review on capturing the condensate along with some essentials concerning the transportation of this medium. So now let's talk about the last reason that we need to concern ourselves with a properly designed condensate return system, and that's the safety issue. And how does condensate impact safety, you may ask? Well, in a condensate return line, which, as noted, is often biphase in its nature, meaning we have a combination of steam and water in the line, we need to concern ourselves with water hammer. And there are 3 forms: hydraulic, thermal, and differential. And I went over these before when we talked about steam, the steam system. But, you know, in a condensate line, the one that we really have to concern ourselves with is thermal water hammer. This type of hammer occurs when the steam in the condensate line condenses, forming a void which is rapidly and sometimes violently filled with water or the condensate liquid at that particular point. You know, it can manifest itself by a sharp pinging sound. You've heard that. But in more serious cases, it's a loud chugging sound, the effect of which can seriously weaken the pipe to the point of splitting or cracking like you saw before, and spewing scalding hot condensate in all directions. Now, it's very dangerous to say nothing about the energy waste. Now, the other thing with thermal water hammer is diagnosing where it's occurring, which is often a problem when there are a number of hot condensate lines discharging into a common. Now, some people have been successful diagnosing the hot spot through thermal imaging and then taking corrective action accordingly. And one such method of correction is installing a diffuser into the culprit's discharge, as shown in the picture on the right, and then blending the effluent with the existing condensate within the common return line. Now, you know, the other possibility is to capture the flash steam directly from the source before the condensate enters the common condensate return line. Now, looking at the pictures on the screen now, you see in the lower left a picture of a high-temperature drip trap connected to a steam user. And this trap could be piped directly to a flash tank, as shown on the right. The condensate could then flash and be vented to atmosphere, then allow the condensate to enter the common, lowering the biphase percentage. Or, you know, why not capture the valuable BTUs contained in the flash by piping the resultant steam, low-pressure steam, to a low-pressure user, like let's say it's a unit heater or heaters. or possibly the DA in the boiler room. But, you know, I want to hastily add, though, if one of these is the choice and is noted, the steam has to be coming from a non-modulating load in order to make sure that the supply is consistent. Okay, that's fine. So how much flash steam can I capture? Well, looking at the formula for calculating percent of flash steam on the top of this slide, and assuming that we have a user, let's say it's a corrugating machine and it's operating at 150 pounds per square inch and discharging into the flash tank at 15 pounds. So going from 150 to 15, you can capture 13% of the energy that would have been vented if you decided to waste it to control thermal water hammer in your common condensate return line. Just waste it. As noted, though, it's not only the BTUs that you waste, but also, as mentioned, the chemicals, the water and sewer charges are all incurred because of the raw makeup water that now needs to be introduced into the system because you lost that steam. All right, here's another possibility. You know, why not take the hot condensate right back to the boiler room using a high-pressure receiver as shown on this diagram? You know, it certainly cures the problem of thermal water hammer because this effluent never goes into the common return line. And therefore, makes this option an excellent choice and one which is often overlooked because of the initial capital expense. But when you properly evaluate against the ongoing costs for steam, for chemicals, for water and sewer charges, something like this can quickly pay off, even when going through a complicated ROI calculation as opposed to a simple payback calculation. And as you see on the screen, these devices work in conjunction with the deaerator in that you feed the boiler directly from the high-pressure receiver, and then the DA feeds this tank with deaerated condensate, which may have seen atmosphere before it got back there, back to the boiler room, or raw makeup water. So these two work in tandem. All right, so now we've arrived back in the boiler room with our condensate properly handled to this point. But the story doesn't end there. We still need to properly contain it for delivery to the boiler while at the same time making sure that our condensate piping stays in good condition. And this takes us to the boiler room support equipment choices. Firstly, I can choose to go with a vented boiler receiver, as shown on the left. It certainly is less costly than a deaerator shown on the right, but it's an energy waster, as it can only handle water below 212 degrees. And normally, these tanks run, let's say, between 180 and 200 degrees, and that's only when they also incorporate a steam diffuser tube to heat the makeup and condensate blend and blend it to this point before being pumped into the boiler. So these waste energy, for sure. And to say nothing about the higher chemical and blowdown costs due to higher percentages of sulfite that has to be added to this boiler water to combat the oxygen corrosion issue. Now, the deaerator, on the other hand, is pressurized and operates over 230 degrees, between 230, 240, maybe even higher. And as such, removes much more oxygen and carbon dioxide from the boiler feed water, cutting down dramatically on the sulfite treatment, which also cuts down on the continuous blowdown, saving BTUs, chemicals, water and sewer charges, and it goes on. So the boiler's tank of storage water, whether it be a vented receiver or a pressurized receiver, becomes a very, very key decisioning point. And you know, I mentioned the DA eliminates the carbon dioxide from the raw makeup water containing carbonates of alkalinity, which when mixing in the DA water and heated turns to CO2. So this then helps eliminate condensate line corrosion in the form of carbonic acid attack. But you know, the DA will not do the whole job on its own. We also still need a chemical feed system in the boiler room to dispense needed chemicals as prescribed by a reputable water treatment expert, and including an amine treatment system, or amine treatment program metered into the steam line. And once the steam condenses, it greatly mitigates the possibility of this carbonic acid attack in the condensate return lines. All right. That really covers the efficiency, reliability, and safety issues that I wanted to cover today, and all associated with designing a sound condensate return system. So here's at least what I would consider to be the main takeaways for today. The boiler is part of a total system, including its piping, supply, and return network, and all the associated accessories supporting the total whole. In other words, it's not just the boiler. If the boiler is not properly piped, interconnected, to be able to efficiently deliver the steam to the users, trap out the condensate, and bring that back as hot as you possibly can, that's what makes a good, efficient, reliable system. So we have to look at it holistically. Proper condensate line engineering impacts energy efficiency, production reliability, and safety. Those are the key issues. And that's why handling this condensate properly is so important, because of those impact areas of efficiency, production reliability, and safety. Every 10-degree pickup in feed water temperature, return that condensate. Remember, the higher the pressure that we're operating under, the higher the amount of BTUs that we have to add to the water to get it to the boiling temperature. And so if we can return as much of that hot condensate, the sensible energy, back to the boiler room, we're that much more efficient, saving countless dollars in the process. Every 10-degree pickup in feed water, 1% pickup in fuel efficiency. Condensate is sensible energy, which increases with increasing operating pressure, as I mentioned. Reliability is affected by system backup or stall and system corrosion. Remember, backing up into that heat exchanger, you're going to reduce heat transfer. The heat transfer coefficient is reduced. The amount of product going through is not heated properly. Lots of problems. And then the other thing is corrosion. Get rid of that air in that system. Condensate line water hammer is normally thermal type. Flash recovery systems can mitigate the problem and save energy as far as water hammer is concerned, but saving energy in the process, equally important. Recommended velocities in biphase condensate lines is between 3,000 and 7,000 feet per minute. As line pressure in biphase condensate increases, the volume decreases, reducing line size for the same velocity. Condensate line sizing involves knowing boiler pressure, trap inlet pressure, pounds of condensate, common line pressure, which is the common return line going back to the boiler room, desired velocity, and desired pressure drop. Remember, that should not exceed 20% of the boiler's operating pressure. Okay, I think those were the takeaways that I had, Susan. So why don't we get into some questions that might have been coming in during this homily of mine.
All right. Thank you, Steve. We had a fantastic crowd today, so I appreciate everybody listening in. At this time, we'll go ahead and take a few questions from the audience. If you will be so kind as to submit them using the Q&A tool on your WebEx control panel, and please send them to all panelists, and we'll have a record of the questions. And today's questions will be recorded as well, and then posted, and there'll be written responses posted and put on our website. Again, if you would like a copy of today's presentation, it will be available at cleaverbrooks.com/webinars. It'll be located underneath today's presentation title, and also it will be in a PDF format. There will be a recording of today's presentation that will also be posted, as well as the Q&A. So keep those questions coming in. We'll try to get to them one at a time in the order that they came in. And if you are using the chat feature, if you'll move it over to the Q&A tool, I'll go with those questions first and then go to the chat tool. It kind of gets a little cumbersome when I'm going back and forth between the two. If you requested a certificate today, it will be delivered to you via email by Friday, probably more likely by tomorrow, but Friday at the latest. And also, if you did not request a certificate but you prefer to have one, go ahead and email us at marketing@cleaverbrooks.com, and we'll be sure to add you to the list. If you are watching the presentation with someone else at someone else's computer and use their login, go ahead and submit that email as well, and we'll make sure that you get a certificate too. All right, Steve, one of the first questions that came in was, explain what you mean by saturated steam.
Okay. Well, saturated steam, it's really saturated water, which has been heated to the point where no additional BTUs can be put into it before it changes state, before it goes into steam. So in other words, once I get to that boiling point of, with the 100-pound example that we used before, 338 degrees, when I add additional BTUs, now that water says, I can't take anymore. I am saturated. And as a result, it changes state. And as I add those BTUs, and I get up to that point where I have now added additional BTUs of latent energy, in that particular case was 880 more BTUs, I now have steam at the same temperature as the water, 338 degrees, but it's now steam. That now has all that latent energy, those 880 BTUs. When that goes out to the user, that user then extracts those 880 BTUs, and what happens, what I have left is condensate, the hot condensate, all that sensible energy that I put into that water to get to that saturation point. So the latent energy does the work out in the system. The condensate is what we want to bring back as hot as we possibly can to our boiler so our burner doesn't have to consume as much energy.
Okay, thanks, Steve. Another question, is it always possible to recover TDS controlling blowdown and save energy?
That's a very good question. You're always going to save energy by doing this. It's always possible, but the amount of the blowdown and the frequency will dictate the payback potential, and if it equals a legitimate return on investment. In other words, you got to have enough mass flow, and you have to have enough mass flow, and it has to be relatively continuous, so we can take that cold makeup water and extract those BTUs from that effluent, that blowdown, that continuous blowdown, take those BTUs out as much as we possibly can before that blowdown goes to drain. It goes through a separator or cooler and then goes into the drain. But let's grab as many BTUs as we possibly can. So does it always work? It always works. What is the ROI there? It depends upon mass flow and temperature, and the mass flow, temperature of that effluent, and how continuous it is.
All right, thanks, Steve. Okay, looking still at the Q&A tool. And if we don't get to every one of your questions, again, we're going to take all the questions that we've collected and we'll answer those and post them on the website. Or if they require a specific response to you directly, we'll be sure to do that. All right, next question. Isn't it possible to avoid stall by properly selecting the right trap with an adequate minimum static head, avoiding the use and cost of a power pump? And let me know if you need me to read these over again, Steve. Isn't it possible to avoid stall by properly selecting the right trap with an adequate minimum static head, avoiding the use and cost of a power pump?
That's a good question, and you know, absolutely this is possible. But many times, at least what I've run into, there's insufficient height above the trap. Just not enough headroom to be able to give us that static head that we need. Remember, we need 2.3 feet of head, 2.3 to get a pound. So that's the differential that we require in low loads for the trap to properly function. So if we've got enough static head, absolutely, we should be able to, you know, determine what would be the most critical, or what would be the absolute worst condition, and see if we've got enough static head to be able to have enough differential in that trap, let's say it's a floating thermostatic or a bucket trap, inverted bucket, to be able to move that condensate out. If you don't have enough room, then you better start thinking about a power pump.
Okay, next question. What is the maximum distance for drip pocket placement in a straight length of pipe?
Well, we like to see, I would recommend, and I've worked pretty closely over the years with Armstrong International, and they say they'd like to see in a linear length of pipe every 100 to 150 feet, never more than 300 feet. You don't want to go 301 feet. If you want to save cost and cross everything at 2, every 300 feet would probably be acceptable. Nothing beyond that.
Okay, can you briefly review the flash steam calculation again?
Yeah, I can. In fact, I think what I'll do is I still have control here. Let me quickly go through this, and I'll go back to this slide. You see the formula up on top. HF1 minus HF2 divided by HFG2. Okay, fine. HF1, that is the sensible BTUs in. In other words, I've got, let's say, as I say in the example here, I've got 150 pounds discharging into my flash tank. And the flash tank is at 15 pounds, let's say. Because remember, this flash tank, once it flashes off the steam, is going to drain the condensate into your common return line. Let's say that's operating at 15 pounds. And then I've got the latent BTUs as far as the 15-pound steam is concerned. So I go to my steam chart. And if I take a look at the sensible energy in on my steam chart for 150 pounds, that's the amount of BTUs I had to bring into that water to take it up to the boiling point. And those steam charts are based at 32 degrees. I kind of cut it for brevity purposes. When I went through my calculation before, I started at 200 degrees. All right, so I need 338 BTUs to bring that up to boiling at 150 pounds. My sensible energy in the 15-pound line is 218 BTUs. So I subtract the 2, and I come up with 120. I then divide that by the latent energy of the 15-pound steam, and it's 946. So when I go through the math, I have 13% flash steam captured. So HF1 is the sensible energy from your steam tables at the high pressure point, at the discharge point from the user. HF2 is the sensible energy at the discharge pressure from your steam table, sensible energy again, divided by the latent energy of that 15-pound steam, again from your steam table, to give you your percentage of flash steam. Now, one thing I wanted to add here is that the lower the discharge pressure, the greater the amount of flash. For instance, if I went from 150 pounds to that zero gauge pressure into a zero pressure condensate return line, if I went through the same methodology, I would come up with 16% flash steam. Okay, so the lower the pressure that you're discharging into, the greater the percentage of flash steam saved.
Okie dokie. Let's take maybe one more question because I know we're at the top of the hour. Again, for those of you that need to drop off, there is a survey at the close of the WebEx. If you would be so kind as to fill that out, tell us how we're doing, tell us what topics you're interested in. We do take that into consideration. If you would like a certificate and you didn't request one upon registration, just email us at marketing@cleaverbrooks.com. And we'll get those out to you hopefully by Friday. And look for the presentation, the recording, and the questions to be posted to our website as well. All right, Steve, last question right now. And again, we have a lot of them that we did not get to, but we will grab those, we'll download them and respond back. So is it possible to have differential water hammer in a condensate line?
For differential, okay. Differential water hammer is different than the thermal water hammer, in that differential is the difference between the upstream pressure and the downstream pressure, wherein you can grab a quantity of water. During the November presentation on steam systems and water hammer, I talked about a bowling ball. Say a 17-pound bowling ball flying down a condensate line at 70 miles an hour. I talk about 7,000 feet per minute. That's actually 80 miles per hour. So it's very, very possible in condensate lines to incur differential water hammer, which can be extremely dangerous. And it's something that we definitely want to be very careful about. And that's why it's so important that we maintain proper velocity and proper line size, condensate line size, to reduce that velocity. That's why I said, boy, the larger the better. So when we have these biphase conditions occurring in our condensate lines and pressure building up, differential water hammer is certainly a possibility and something that we want to avoid at all costs. And that will be a matter of trying to reduce the amount of biphase that we have, the percentage of biphase that we have in our condensate return line, as well as properly sizing or oversizing that condensate return line to be able to minimize the amount of velocity in that pipe.
All right. Thanks, Steve. Thanks again for a great presentation, and thank you all for joining us. And check back on our website to see when the next webinar will be and what the topic will be, and the registration should be up for that shortly. I do want to say a big thank you to some of our top attendees. I know ConAgra had a lot that showed up today. Very, very pleased to see that. Dow Chemical was probably one of our biggest attendees. Hartford Steam, just appreciate you all being with us. Even Boiler Supply, one of our manufacturers representatives, I think you topped the grid this time for our inside participation, so appreciate that. Nexet, good attendee, consistent. We see a lot of you guys and gals on every month, and we do appreciate it. Siemens, as always, too, a big participant. Just scrolling down the list here. Train. Yeah, got a lot of people from individual states too, so state systems, universities. I appreciate you joining us. All right, well, we'll wrap up with that. Thanks, Steve. See you again possibly next month, and let's look for the next topic on our Cleaver Brooks website. If you have any questions, go ahead and send them in. You can send them to marketing@cleaverbrooks.com, or you can send them to webinars@cleaverbrooks.com. And I think even my name and email address, contact information is available through part of the registration email. All right. I appreciate everybody joining us, and we look forward to seeing you next time. Thank you very much. Thanks, Steve.
You bet. Bye-bye.